Okay folks, let's talk about this chemistry paper. Some of you need some help to go through this, I think. So we're starting off here in the middle of the Year 10 exam on the higher tier chemistry paper. The question is talking about lithium reacting with water to produce hydrogen gas. And we've got a diagram showing an experiment. Now a good tip here is to look straight to the question. What are we being asked to do? Suggest is the command word that I'm highlighting. It means have a decent stab at coming up with a reason why the lithium is wrapped in copper gauze. So I would be thinking here, facts about lithium, group 1 metals, they float. So if you look in this diagram, the fact that the lithium is down here is unusual because normally it would be floating on top of the water, and so the copper gauze has made the lithium sink. Okay, so hopefully you can see from my answer that I've written here, I've said explicitly that the lithium is being made to sink by the copper gauze. Notice I'm not using the word it in my answer because that could be misinterpreted by somebody marking it. Part 2, one product of the reaction between lithium and water dissolves in the water to give an alkaline solution. Now, the key idea here is the word alkaline. Facts about alkaline, they are caused by hydroxide ions. So when I see the word alkaline, I'm thinking to myself, it's going to be something hydroxide when I write my answer. Lithium is reacting with water, and the product will be lithium hydroxide. I know that will be an alkali because hydroxide ions make things alkaline, a pH greater than 7. Okay, part 3 of question 3. The experiment in figure 5 is repeated using 0.14 grams of sodium instead of 0.14 grams of lithium. So I'm interpreting from the fact that this mass is the same that it is not the difference in mass that's going to cause a difference. It tells me that a smaller volume of hydrogen gas is produced. Give one other difference that can be observed when sodium is being used instead of lithium. So in other words, let's compare what we know about sodium and lithium. We know that sodium is more reactive than lithium because it's further down group 1. If we thought of the elements in group 1 and we wrote down the first 3, we know that as you go down the column, they get more reactive. Sodium is more reactive. I'm looking for something that would be observed. In other words, what would I see? Sodium is more reactive than lithium. I would see faster bubbling. Would be a good answer here. You also might recall that the sodium melts into and fizzes around on the top of the water as a ball. Okay, I think this is the most likely answer that you would come up with. Sodium is more reactive than lithium. It will bubble faster. Okay, we've got figure 6 showing what happens when sodium reacts with oxygen to form sodium oxide. The diagram reminds us that the dots and crosses represent electrons, and the command word in this question here is describe. Describe what happens when sodium reacts with oxygen. You should refer to electrons, atoms, and ions. These are the sorts of questions where we need to be very precise with our language to get full marks. We're aiming for 4 marks. We're going to try and write 4 clear bullet points to get maximum marks here. So let's think about what's happening. So first of all, and I'm going to answer mine in bullet points here, that the sodium here are atoms, as is the oxygen. The sodium atoms transfer electrons, and you can see that in the diagram. The electrons are going to the oxygen atom. Look at the diagram. We can see that here the oxygen has got 2 crosses added to its outermost shell, and the sodium atoms have lost their outermost electron, and that's because they've transferred them to the oxygen. That means that the sodium and oxygen have changed. They're no longer atoms, and they have become ions. Remember the definition of an ion: an atom that has lost or gained electrons becomes an ion. The sodium have become positively charged because when you lose electrons, you make positive ions. Losing is positive. The sodium atoms have lost electrons and become a positive ion, whereas the oxygen atom has gained electrons. Gaining is negative. The oxygen becomes an oxide ion. So we can say each sodium atom loses 1 electron to become a 1+ ion, whereas the oxygen atom gains 2 electrons and those 2 electrons are going to fill up the outer shell. It's going to make a 2-, and we change the name of non-metals. Oxygen becomes oxide ion. Finally, notice what's happened here. For both sets of the ions, all of the shells of electrons are complete. So we could say that all the ions have full outer shells, or we could write the general rule for ions, which is that the ions have the same electronic arrangement or the same electron arrangement as group 0, the noble gases. It's a good rule to learn. Whenever an atom becomes an ion, its electron arrangement will mean that the outermost shell is full, and that is the same as group 0, the noble gases, helium, neon, argon, krypton, etc. Okay folks, another classic question from chemistry. We've been given information: sodium oxide melts at a temperature above 1000 degrees Celsius. Sodium oxide is an ionic compound. We could just ignore that because this is what we're doing. We're explaining why ionic compounds have high melting points. Okay, think what it means to melt. Melt means that the forces between particles have to be overcome so that the particles can move around each other and swap places. So the key thing about ionic compounds is they have a giant structure. Many, many ions all held together. The giant structure is important because by saying giant, you're saying that there are a lot of forces. There are many strong, keyword coming up, electrostatic forces. And those are holding the ions together. Think what that means. It means the positive ions are attracting the negative ions in all directions, making this giant structure. Let's finish off with our explanation. Therefore, a lot of energy is needed to make it melt. Okay, question 4, next question. The information tells us that the relative atomic mass of an element is a comparison of the mass of atoms of the element with a standard isotope. We're asking to recall a fact here. When you say relative mass, it means relative to something else, and it is relative to carbon 12. All relative masses are relative to, that means compared to, the mass of 1/12 of a carbon 12 atom. And if you think about that, 1/12 of a carbon 12 atom equals 1. So this is our definition of the value of 1 when it comes to comparing the masses of atoms. 4.2, we've got a word in bold. I'm thinking, what am I thinking of? What's in my head about the word isotopes? I've learnt my definition of an isotope. What does the term isotope mean when referring to atoms of the same element? It means they have different numbers of neutrons, the same element with different numbers of neutrons. Okay? The only thing that's different between atoms of the same element will be the number of neutrons. In other words, they've got the same proton number, but different mass numbers. The same number of protons means the same element. Different numbers of neutrons means different masses. Different masses is what an isotope is. 4.3, we've got a table with 2 isotopes of chlorine. So you can see what I'm talking about here. They're both chlorine because the proton number is 17. They're isotopes of chlorine because the mass number is different. This chlorine atom has 17 protons, as does this one. So if I was talking about the number of protons here, this chlorine has 17 protons and 20 neutrons, because those two numbers added together make 37. Whereas this chlorine also has 17 protons, but it only weighs 35, so I only need 18 neutrons to make up the 35 mass of this chlorine isotope. The relative mass of chlorine is 35.5. If you look on your periodic table, it actually shows that, which is quite strange, because you can't have half a proton or half a neutron. So the reason we've got 35.5 here is it's an average. If I added all the chlorine together in the world, the average mass of a chlorine atom is 35.5. Now, because that number is closer to 35 than 37, that gives us our second point to make. We've got 2 marks here, look. The second point is to say that the chlorine 35 isotope is more common, or more abundant would be an even better word. Okay, there's a greater proportion of the chlorine in the world, weighs 35, compared to the rarer form of chlorine, which weighs 37. Okay, next part of the question is talking about chlorine gas. Simple molecules that's represented here, and I'm being asked to explain why chlorine has a low boiling point. So low boiling point straight away. Why has it got a low boiling point? Because not much energy is needed to hold the particles apart. Little energy is needed to overcome the forces between the molecules. Okay, that means, if not much energy required, that the forces between molecules, keyword coming up, weak inter, that means between, intermolecular forces are weak. Chlorine has a low boiling point because the forces between molecules are weak. It doesn't mean that this bond is weak. This is a strong bond. It means that when there's another chlorine molecule nearby, there's nothing attracting these molecules together. They're not going to be held together in some sort of giant structure, so we say they have weak forces between the molecules. It's easy to keep this Cl2 and this Cl2 apart, so it has a low boiling point and it will be a gas at room temperature. Okay, question 4.5, I'm going to be completing figure 7, that's here, to show the arrangement of outer shell electrons in a molecule of chlorine. Use dots and crosses to represent the electrons. So I'm thinking here that chlorine is in group 7, and so it's going to have a total of 7 electrons. 1, 2, 3, 4, 5, 6, and I need at least 1 in here to make a bond. Okay, if I do the same for this chlorine atom over here, 1, 2, 3, 4, 5, 6, and 1 in this shared space in the middle, I've shown exactly what this diagram up here shows, which is a covalent bond between 2 chlorine atoms. A covalent bond is a shared pair of electrons. So my diagram scores 2 marks because I've got 2 electrons in the shared space making my covalent bond, and I haven't forgotten that there's another 6 electrons that aren't involved in making a covalent bond that would be present in the chlorine atom. I know my diagram is correct because by having the 2 electrons in this shared space here, this chlorine atom now has a total of 1, 2, 3, 4, 5, 6, 7, 8, a full shell, and this chlorine atom also has 1, 2, 3, 4, 5, 6, 7, 8, a full shell. By sharing 1 electron from each atom, both chlorine atoms end up with the same electronic arrangement as group 0. They have a full shell and they've become more stable. The final question in this chemistry section here is asking you to use a little bit of thinking. The relative formula mass of chlorine, Cl2, is 71. That's because most chlorine is 35.5 on average plus 35.5 on average, which equals 71. Some chlorine molecules have a relative mass of 72. I'm looking back in the question to my original information over here. Chlorine 35 plus chlorine 37, if those two join together, then I would end up with 72. Okay, so the reason why some chlorine molecules have a relative mass of 72 is because a chlorine 35 is bonded to a chlorine 37, which equals 72. Cl2 made out of 1 of these and 1 of these to give a total mass of 72. Okay, finally from me folks, I'm saying to you, let's sign up to Cognito, make yourself a free account, check out the chemistry and have a look through this section on bonding, structure and properties of matter, particularly the ionic and covalent bonding sections if you haven't done as well as you hoped in this test.